Hi, my name is Bin Kim. I'm a research scientist at Google Brain Team. Today I'm going to talk about my hopes and dreams. I'm sure many of you have dreams too, what AI can do, what they can become, things maybe once you saw in sci-fi movie or a novel, things that you keep coming back to whenever you need just a little bit of more fuel in your motivation. I would like to share a bit of my hopes and dreams and small steps we took towards it. You're in this room, you absolutely probably know about these all surprising things that AI can do, including more recently generating images given a simple text prompts. If you like John Oliver, I'm a big fan. You might have watched this episode where he shows highly entertaining generative pictures of him and the cabbage. Why cabbage? You should watch the episode, highly entertaining. And this advances of just how much AI can do is pretty impressive. But it's not kind of dream that I have, hopes and dreams, when I started my research in AI. Instead, I am just curious about this AI. I want to talk to them. It's just like if you meet someone new, maybe someone from different background, someone you find fascinating or admiring, you regard to ask some questions. How are they doing all these remarkable things, whether that's solving decades of protein problems or beating a world gold champion? Does it view the world differently from us? Does it have the same language of science and medicine, like molecules or atoms, when it solved the protein problem? How is the food that we provide to these aliens, these machines, data and computing power, creating this remarkable capacity and capability? How is it different from how we solve the same problem, and how can we work together? One concrete conversation that I really would like to have is with AlphaGo. AlphaGo defeated the world gold champion Isidore in 2016. I watched every single match. And in one of the matches, AlphaGo made this now famous move called Move 37, which Nine commentator, when this move was made by AlphaGo, I remember him saying, that's a very strange move. But it turns out that move turned around the game to favor AlphaGo. And Go players to this day talk about and trying to analyze this move. And some might refer to it as Move 37 was beyond what any of us can fathom. So how does AlphaGo know that this was a good move? My dream is to understand fascinating behaviors like this one, to learn something new by having a conversation, such that the humanity will gain a new angle to approach to many of the important problems in science and medicine and many others. So how do we have this conversation? Conversation assumes that we share the same vocabulary and language to exchange meaning and ultimately knowledge. And naturally, representation plays a key role in thinking about this problem. What machines know, machines' representational space, and what humans know, humans' representational space is very different. And we can visualize this. The circle on the left represents what humans know and their representational spaces. For example, when I say, hey, this dog is cute, you roughly know what I meant by that. On the right hand, we have representations of what machines know. There's probably some overlap between the two, but it's likely that there are things we don't yet have a representation for, just like that Move 37. What are these Move 37 things in robotics? Well, it doesn't have to be always about superhuman behavior. It can just be non-human-like ways how robots reason about the world. For example, how do they parse, digest human demonstration and imitation learning? How does autonomous cars see and represent pedestrians? Well, there's a typo there. And understanding these sort of how machines think about the world help us design better robots. So how do we have this conversation? Our representational space needs to overlap. The more overlap we have, the easier to develop this language that we both use to have that conversation. We can do this by maximize the overlap, by expanding what we know through dialogues, collaboration with machines. And learning more about machines will enable us to build machines that can better align with our goal and have the better conversation. If you're curious about some work we've done towards as the first few steps towards bridging this gap between what we know and what machines know, my iClear keynote this year is online. It's also on my webpage. It's a great resource. I'm not going to talk about a lot of this work in this talk. Instead, we're going to talk about the hopes and dreams, understanding the Move 37. As we think about how to realize this dream, first we have to ask, do we have tools to estimate what machines know? It's the purple circle. The machine learning community has developed many tools over the years to understand what machines know. Is that tool accurate? Unfortunately, recent evidence has shown that these tools don't work as expected, and we'll talk more about this later. In other words, there's a gap between what machines know and what we think machines know. Then that means that we don't have the full picture of what we're measuring from these tools that reflects what machines know. And identifying and bridging this gap is the first step in having this conversation, because these tools will form the basis of realizing that hopes and dreams and that conversation. So brief overview of what are these tools? Well, an example of this tool is called saliency map. Suppose we have an image classifier predicting what's in the picture. This is predicting there's a bird in the picture. And saliency map for that picture looks something like this. Each pixel is highlighted, indicating how important each pixel is for a prediction. The definition of how importance is different depending on the tool you're using. But essentially what it's trying to do is trying to find the shape of your function, the classifier in this case, around that pixel. So for example, if this pixel that is not highlighted is called xj, we're trying to figure out whether the function f of xj goes up or down or flat around this feature, in this case, pixel xj. Now, there might be few different reasons why this gap exists. First, we might have wrong assumptions about these machines. We humans understand and respond to the world in a certain way, and we may assume that machines do the same thing or perhaps differently. Perhaps those assumptions are wrong. To address that, studying machines as an independent organism in isolation from humans is useful. Some of the work we did to investigate whether neural network has this Gestalt phenomenon that is a very strong visual phenomenon for humans. The answer is yes, they do, just only when they can generalize. Second reason for this gap might be that our expectations are misaligned. Maybe the tools are not doing things that we think they're doing. We're going to take a deeper dive in one of this work in this talk. Lastly, it might be that whatever explanation that these tools are extracting are beyond our comprehension. Maybe we just simply can't understand. It's there, but we can't understand. Now, we've done a few work to place these explanations in front of humans and gave them a task. We intentionally insert bugs in the model and ask humans, can you tell there's a bug? And these tests, it surfaces that some of this information, assuming that they exist in the explanation, is not something human can digest. So in this talk, however, I'm going to go on a deeper dive into this one work. It's very recent work. It's actually not on arXiv yet, but it's a very exciting result, so I'd like to share. So TLDR of this work is that our expectation of these tools are misaligned. And again, bringing back what these tools are doing, there's a goal. The goal is to understand the shape of the function around this pixel. For example, if this tool assigns 0 attribution to a feature or a pixel, then we want to infer something about the function shape, maybe the slope. Now, typically, this is how these tools are aiming to do and how these tools are used in practice as well. Here's a quote from one of these tools that we study in this paper, Integrated Gradient, that says IG can be used for accounting the contributions for each feature. Some of the medical paper oncology understands and uses these tools as such. The Shapley value, another tool that we study in this paper, Shapley tool value close to 0 correspond to eligibility criteria that had no impact on the criteria for a medical trial. So what they're doing in these quotes is that when the tool assigns 0 attribution to a pixel, then folks are inferring, well, that pixel is unused by the model, or that this function f is insensitive to perturbation of this feature near x. Those are inferences being made and used and claimed. In this work, we show that many of these inferences are wrong, that we theoretically prove that these inferences seems pretty natural that people reach. Actually, none of these tools can inform those inferences. So just because that tools assign zero attribution does not mean that you can conclude the model isn't using the feature or that function is shaped such that the function is insensitive to perturbing at that point X. In this work, we also show that what are the conditions under which these expectations do become aligned. If this is a space where we thought we have aligned expectation, how do we carve out this space and provide mathematical characteristics where these guarantees can be met? So a lot of more work to do to bridge this gap, whether by questioning our assumptions when we build these tools, aligning our expectations, and determining when some informations are simply not comprehensible by humans. But we started this talk by talking about my hopes and dreams, the Move 37. So instead of trying to build a tool to understand what machines know in that full space, what if we develop methods to specifically probe at this alien to see what they know, treating it like a new species that we developed? There's a few different ways to study aliens. Luckily, this alien doesn't mind if we investigate their internals, and we can do some surgery without hurting the alien and investigate their internals. The alien is made out of numbers, vectors, and we have math, the tool that we can use to analyze those numbers. We can also just watch them, observational study, where we view their behaviors in the wild nature and try to infer something about their behavior, emerging behaviors. We can also do controlled study, where we can directly intervene, and these aliens don't also mind if we put them in the controlled setup. And by intervention, we try to infer some internal behaviors of these aliens. So those are the works that I'm going to take a deeper dive into. First, surgery. This is the work we did with DeepMind in studying AlphaZero, which is a superhuman chess-playing machines that could beat any existing human experts. This is, of course, a model from DeepMind, and our collaboration was with DeepMind and a world chess champion, Vlad Kramnik. So self-trained means that it was trained by playing against itself. That means that it never ever saw how humans play chess. And this is interesting because if we can show it naturally learns to share some vocabulary with us, that gives a hope to expand what we know and learn that new Move 37, if such thing exists. And this AlphaZero is not just any self-trained chess-playing machine. It plays it really, really well. It beats the Stockfish engine, which is arguably the best chess engine out there, after only 4 hours of training from scratch. And we were fortunate to have Vlad, a former world chess champion and a co-author of this paper, who has a better chance of talking to this alien than any of us and provide us some qualitative insights. The first question is, do human chess concepts exist in AlphaZero? Or does it just learn to play in a completely different way? It turns out it does, but what concept is learned when and where varies. Like some material imbalance is learned and forgotten as AlphaZero gets better at playing, whereas in check, which is a pretty critical for winning the game, stays learned throughout. And what's interesting is that one can argue that material imbalance is something that novice chess player like myself used to play at first, but the experts know that imbalance isn't enough to win the game. And it seems like AlphaZero goes through the same phase too. These concept definitions mostly come from third-party APIs. The Stockfish engine offers a concrete function where you can use to extract these concepts, along with our own defined concepts. Thanks to the database from ChessBase, we can also compare the evolution of human chess playing versus AlphaZeros. The left graph is showing the proportion of different opening moves and how they evolve over pretty much the entire recorded human history of chess since 1400. And on the right, we're showing AlphaZero's opening move evolve as the training steps. They look pretty different. It's particularly interesting how AlphaZero has much more diverse moves than humans. In other words, this might mean that if humans are trying to win AlphaZero, they would have to master a lot of different strategies stemming from different opening moves, which is I find it fascinating. And of course, different random seeds trained AlphaZeros leads to a similar distribution of opening moves, very diverse. It's also interesting that there seems to be a point when things click for AlphaZero. This is widely known as grokking in machine learning community, and it happens in large models. And this happens to AlphaZero too. And it also chooses the style of play. And this explosion of skills, it aligns well with Vlad's qualitative assessment and our quantitative observation. Finally, we take some first steps to expanding what we know. We use non-negative matrix factorization, a pretty principled technique to decompose AlphaZero's embeddings. And we look at how each components in the decomposition look like in the input layer. And this is only possible because of this special structure in AlphaZero. In AlphaZero, every latent layer has exactly the same dimension as the input space. So we can project that back to the input space and look at what it might have looked at. This is a small step, but because validating a new chess concept is likely to require many more than one world champion, so that will take time. But in the meanwhile, we build a tool that lets you explore AlphaZero's representational space. It's an interactive tool. You can find a tool in my website where you can look at every single components that we've discovered and explore interactively. Second work that we're going to take a deeper dive in is observational study. Now we're going to switch gears a little bit to think about not chess, but multi-agent reinforcement learning setup. Emergent behaviors in multi-agent system has been fascinating. The hide-and-seek OpenAI, which we're going to look at it a little bit more carefully, the football players, and capture the flag, all of which describes this really interesting behavior naturally emerges in multi-agent setting. This is one of my favorite examples. Here we are showing models that are trained by OpenAI and labels of emergent behaviors done by humans. So running and chasing, fort building, ramp use, these are all labeled by humans and provided by OpenAI. They first observe running and chasing, pretty natural behavior for hide and seek game. The blue agents are hiders, the reds are seekers. Fort building, blue agent build a fort around them to protect themselves. But then ramp use, the red agent learn how to use the ramp to get over that fort to still find the hiders. But then something interesting happens in the middle of the game, box surfing. It turns out that the seekers can surf the boxes, this is the E, box surfing, to get to the fort. And of course, then hiders learn how to lock those boxes so that the seekers can use those boxes to find them. It gets just really interesting and looking at all these emergent behaviors, but remember that this required a lot of manual labeling and scrolling through these videos for humans. So the goal of this work is to automate the detection and visualization of these multi-agent behaviors. And again, we're treating these agents like animals in the nature. So problem is, given the state action trajectories, we can only observe where the agents are, for example, what are the actions they took. And then goal is to discover agents' behavior using clustering-based approach. This is our work published in Europe this year. And our approach, which we call multi-agent offline hierarchical behavior analyzer, short for MOBA, is training a generative model to discover joint behavior latent space, also local behavior latent space. What do I mean? So Z omega on the top represents what are the overall behavior trends that appear in the whole space. For example, it can capture whether the agents are working cooperatively or competitively. Then we also learn latent behavior space for each agent. So what are the skill sets each agent acquire in the course of the game? Then conditioned on that, we can generate policies. These are all learned behaviors, the Z omega, Z alpha, and pi, which are learned from our observations, states, and action pairs. And we simply do this by lowering the variation lower bound, optimizing for JLB here. Pretty common approach. So we did this for many interesting environments, but for now, let's look at a domain called Mujoko. This is training two agents. It's a cheetah. It's trying to learn. Agent 0 is in charge of the back leg, agent 1 is in charge of the front leg. And on the right, you're looking at the joint embedding space and the visualization of it. You can also see it in this website. Visit here or look at the paper for the link. Now we're going to select some of these parts in this joint embedding space to see if we can discover something interesting. So first of all, I just selected this lower bottom space in agent 1, which maps to a pretty tight space in agent 0. It seems to show the space where both agents did learn how to run proficiently. On the other hand, this space right here that I just selected seems to show that agent 1's environment is pretty tight cluster, but it's kind of spread out for agent 0. And that seems to show not as good of running skills learned by them. And I've seen this a few times across different applications that we used. Perhaps the one-to-many mappings from agent 1 to agent 0 represents how those two are less coordinated than we wish them to be. So those are really interesting. And here's some other trajectory that you can see. Also seems to map into pretty tight space, good running experience. We also applied MOVA on the OpenAI hide and seek space, my favorite, 4 agents, 100-dimension observations, 5-dimensional actions, and 200 decision steps. These are all openly available by OpenAI, as well as 4 human annotated policies, such as the following: running and chasing, ramp use, fort building, and ramp defense. Now, what's interesting here is that if you look at the local agent latent space, the ones in the bottom, blue dots, the running and chasing, pretty fundamental to hiders and seekers, all pretty distinct clusters. Whereas the green dots, the ramp use, seems to be more distinct for seekers, which makes sense because seekers are the only ones who are using the ramp, but perhaps hiders could have developed that more distinctively, but in this case, it seemed like it didn't, which is very interesting. Dirty laundry slides for this work. Remember, we are only showing you an easy way to detect potential emerging behaviors. We don't give you names of these clusters that you can see in the visualization. Humans still have to come up with those names. However, we're hoping that this offers acceleration in discovering such clusters and therefore the names. If the cluster is way too complex that it's hard for humans to digest, again, same problem as we discussed before. If it's beyond our comprehension, this method cannot help you. If you do have rewards and internal representations, you should use it. This work doesn't use it and may not be the best fit for you. In our next work, however, we do use it. So next up, we're going to talk about controlled study in studying this alien. Here, goal again is to understand multi-agent behaviors via intervention this time. So the goal problem here we are solving is let's build a multi-agent system such that it enables the controlled testing, but performs as good as if we didn't have those new plugins that we use to enable controlled testing. There could be many different approaches in doing this. The one we use is leveraging previous work, concept bottleneck models that we worked on with some of our co-authors, where the idea here is pretty simple. You have a model. We're going to build in the concepts in one of the bottlenecks in the model so that, let's say you're predicting a zebra, you may have concepts of trees, stripes, and lion. What's the benefit in doing this? Well, when you have this, you can at inference time control and cancel out. For example, I don't think trees are important in predicting zebra. I'm going to zero them out. And that's a pretty simple idea. And that's the one we leverage in this work, although in reinforcement learning settings, so it's a lot more complex. But this time, the model is taking the RGB value of the game and convolution net, positions and orientation. And you have concept estimates in the bottleneck that a whole network spits out an action. We again assume these concepts to be pre-labeled and available for us. So for example, in this domain is a melting pot. There's 2 agents, yellow and blue. They are trying to make soups and deliver soup. We have a pot, we have a dish. They pick up tomato, put it in a pot, wait for a while until soup is done and serve the dish. So the concepts available in this space for us is agent's positions, orientation, whether agent has tomato, dish, or the soup. The way we train this model is we train such entire architecture per agent, and we minimize the typical PPO, proximal policy optimization. And in addition to that, we have a concept loss function where we trying to match the true concept label with estimated concept. And we have lambda coefficients to try to balance out the two. What's good in this? Well, again, with this concept bottleneck, we can intervene one of the concepts at inference time, and that creates this controlled testing environment where we can test the counterfactuals. What if the agent did not have a misinformation about this other agent? What would happen? With which we can reveal some interesting behaviors, as I'll show you soon. So first question that we can answer is how much they coordinate. So this environment on the left is a basic environment. They can choose to coordinate or they don't have to. We created passable environment where there's asymmetric resources. So yellow agent is a lot more closer to pots and dishes than the blue agent, who is a lot closer to tomato. So it's a lot better for them to coordinate so that blue agent gets the tomato, yellow agent makes the soup and serves the soup. We can also make an impassable environment where they have to coordinate because the only way to serve soup is by passing the soup from the blue agent to yellow agent and ultimately to serve. And by enforcing this coordination, our intervention methods successfully reveals the environmental demands for coordination. In this graph, you're looking at what each agent's intervention, their resulting reward when we intervene versus when we don't intervene. And as you can see, there is much more greater degradation in performance in the impassable environment. So in other words, if we intervene each other's concept space, when they are coordinating, there's a lot more degradation that we can observe. We can also observe the degree of coordination via this intervention method. It gets really interesting when we start to look at how they coordinate. So here, this is the same graph. I'm just showing you intervention results per concept. So in this environment, the two agents coordinate to some extent. The yellow agent getting the tomato to the soup and blue agent is getting that soup and serve the soup. It turns out, when I look at this domain, I would assume that blue agent and yellow agent are coordinating based on maybe whether the agent has a soup or based on where they are. But it turns out that's not the case. In this particular training episode, it turns out that they're using each other's orientation to coordinate, which is kind of interesting. So when we intervene in orientation, that's the only time that we see huge degradation in the team's performance. It might make sense in hindsight that when you're heading somewhere, if the yellow agent is coming from the tomato to the soup, they have to look at the soup before they move. So perhaps that's like the earliest information that the other agent can get, that the yellow agent is about to go get the soup. This unintuitive findings like this one is exactly what this framework is aiming to achieve, so that you can learn something about how they coordinate, how this emergent behavior appear, and what is the communication like between these agents. You can also figure out whether there's a free riders, of course, when there's a coordination effort. On the right-hand side, these are all the same environment, though sometimes yellow agent decide to just chill in the corner. There's no movement at all, whereas sometimes, like the one example that we saw in the previous slide, they have a strong coordination. And we can exactly reveal this degree of laziness of the other agent in this intervention methods. And these are the things, again, when you spend a lot of time as a human looking at it, you might be able to guess that the two environment in the middle, the moderate coordination and no coordination, you can tell. However, here is an easier way via intervention where you can just immediately see how much they're coordinating. Now, 30 laundry slides. Our work we show matches the PPO performance, meaning that if we don't just worry about concepts at all and train it as if just regular RL environment with PPO, it matches with the performance. However, we do tune the lambda, how much of importance of the concept that we enforce to the model, and it seems to be some tuning required, so as any other models that you may have. The concepts we use are assumed to be predefined and available. So you do need these where agents are, where orientations are. We are currently trying in a lot more complex domain where the task itself is very complex, but you only have very primitive set of concepts. And we're trying to figure out whether this approach still works, and we're very optimistic. So to wrap up, today we talked about our hopes and dreams, or my hopes and dreams, and hopefully now your hopes and dreams as well. First, we talked about improving tools we use to understand these machines, whether examining the assumptions we have, aligning expectation, and examining ourselves to see whether the information presented in front of us are digestible by humans. We then talked about studying this alien in isolation, doing surgery in AlphaZero case, the chess machine, or observational or control study in multi-agent setting. With that, I hope to see you soon at the virtual workshop. Thank you.